Hey everybody, welcome to your next homework recording. So the next section of this introductory unit on motion deals with something that certain books refer to in different ways. Some books will refer to them as kinematic equations. Your book refers to them as the suvatEquations, and we'll see why that is here in just a second. But recall from earlier in this section on motion, when we are dealing with motion, when we are describing motion or the study of mechanics, there's three things that we want to know. So the first thing is where, right? Where is this object? Sorry, that's sloppy, okay? And we learned that that could be position or it could be displacement, right? Depending on if our object is stationary or whether it's moving. And then the next question that we talked about was what? What is that object doing? And we learned that that's called velocity. And it could be speed depending on how detailed we want to get with it. All right? And then the next question is what next? What will happen next? And we haven't talked a whole lot about it. We've mentioned it in passing, but we'll talk much more about it this week, and that deals with acceleration, right? Where acceleration is the change in an object's velocity over the time that it takes for that change to occur. So remember where, what, and what next. And then the last thing that we worry about, when are all these things happening? And that's our time function. So our suvatEquations are relationships between these different factors that describe the motion of an object. But like it says here, and I believe it says it on the next screen, right? This only applies, these relationships only apply to motions that have uniform acceleration or constant acceleration. That means something is constantly speeding up or constantly slowing down. The changing direction thing we'll talk about more in detail because it's a little bit different, but something is continuously speeding up or continuously slowing down, these relationships apply. So like it says here, again, only work when the acceleration is uniform or constant, right? Those two things are synonymous. But our suvatEquations are mathematical relationships between displacement and then two velocities. The initial velocity, which they call u, not exactly sure why they picked that letter, but then the final velocity of a motion, which is v, then acceleration and time. Notice S-U-V-A-T, suvat. What we find is that how these quantities are described and defined may mean that when one changes, a lot of the other ones change too, because they are all interrelated. And because of the way they're defined, we find out that there are mathematical relationships or equations that show how a change in one gets into or causes a change in the other one. But again, really important to remember, this only applies when our acceleration is uniform or constant. And for most situations, especially at the beginning here, that's going to be the case. I'm not going to throw you a situation where the acceleration isn't uniform or isn't constant, at least not at the beginning. If it is, I'll make it very, very known to you. So let's get into this and see how it works. What we find is that when we are deriving these relationships, they are all based on three equations or three relationships that we're already familiar with, that we have introduced and we have discussed already. Now, I'm going to show you how we can manipulate these equations to end up with the relationships or the final equations that I'll show you at the end. I'm not going to hold you responsible for actually deriving them, but you can see mathematically how it works. It's a lot of algebra, and that's okay, but and there might be some steps I skip along the way, but that's all right, as long as you end up with the equations at the end, just so you know where they come from. So first, this relationship for average velocity. We define average velocity as displacement over time. And remember, the S is what is representing displacement. The T is representing time, so displacement over time is how we define average velocity. And in earlier videos, we talked about the difference between average and instantaneous, but it's still velocity is always a relationship between displacement and time. The second relationship is acceleration, and acceleration is the change in velocity over time. And whenever we talk about the change in something, right, whenever we calculate the change in something, we need to know its initial condition and its final condition and look at the difference between them. So V final minus V initial, it just so happens that your book uses different notation. Remember, V stands for V final, U stands for V initial. So acceleration is equal to V minus U over T. That's a relationship that we've discussed. And then the last one, although we haven't discussed it in great detail, hopefully mathematically it makes sense. Another one, again, it's still an average velocity, but in this case now we're looking at, whereas acceleration deals with the change in the velocity, when we calculate the average of something, just in math class, right, we add the numbers together and divide by how many numbers there are, right? That's how we define an average. We can do that with measurements as well. So in this case, to find the average velocity of a motion, as long as it's accelerating uniformly, if we know its initial velocity and we know its final velocity, that's two velocities. If we add those velocities together, divide by the number of velocities we know, which is 2, we can figure out what the average velocity of the motion during that interval was. So 3 relationships, 2 for velocity, 1 for acceleration, that we have introduced before, and by manipulating them, we can see how changes in one factor cause changes in a lot of other factors when describing that motion. So let's start with the first one, right? Here we start off with our definition of acceleration. V minus U over T, or V final minus V initial over the time it takes for that to happen. So all we do is rearrange that equation and get V by itself. And when you do that, right, multiply both sides by T, right? I should probably use a different color for that. We'll go red, right? So if we multiply both sides by T, that gets rid of our T over here. We're left with this. We add U to both sides, and we end up with this equation right here. V is equal to U plus A times T. Notice, because this relationship started with our definition of acceleration, displacement doesn't appear anywhere in this equation. And you'll see that that's sort of a running theme, and we'll talk about why that's important towards the end of the video. So this is the first relationship. It talks about, it deals with figuring out how fast something is going after a certain amount of time if we know the initial velocity, or how fast it was going initially, and how quickly it was accelerating. So here we're talking about trying to find the final velocity of something. Now, as will be the case several times in this class, we can look at something algebraically, but there are other applications that will verify what we've done. And if we go back to this picture, notice we're still on equation number 1, right? We haven't changed equations, just looking for another way to define this. Here is a velocity versus time graph. And hopefully you remember that on a velocity versus time graph, the slope of that graph tells us the acceleration. Mathematically, we look at slope as rise over run, right, or the change on the y-axis over the change on the x-axis. If we apply that to this equation specifically, right, here's v, right, that's the final velocity. Here's u, that was the initial velocity according to this graph. The change on the y-axis is v minus u. Then the run axis is time. It started at 0, it ended at time t. T minus 0 is t. Again, we can rearrange that equation. Oh, hold on. Sorry about that, technical difficulty. We rearrange that equation and we end up with exactly what we started with. Or, again, we're still on, goodness gracious, sorry everybody. Sorry if I'm making you dizzy. We're still on equation number 1. This is it's a bad stretch right here. Hopefully you guys will be able to work through it. I apologize. We're still on equation number 1. We haven't changed equations yet. Just another way of representing the same thing, right? Y equals mx plus b is slope-intercept form of any straight line. If we then start applying the slope-intercept form to this equation specifically, on the y-axis, we have velocity, or whatever the velocity is over time. The slope of this graph we've already established as acceleration. On the x-axis, we have time. So we substitute in t in there, right? And then the initial velocity, in this case the y-intercept, is the initial velocity. So now we end up with that same equation again, right? Just getting at it in a different way. But the whole time, keep in mind, right, it's a relationship between how fast will something eventually go versus how fast it started, and based on the acceleration and how long it accelerated. Okay. All right, so that's first one. And recall from a couple slides ago, right, displacement doesn't show up anywhere in this equation. All right, equation number 2. So now we're looking at something different. We're looking at finding something different. So I'll change colors here so we get something different, okay? Recall on a velocity versus time graph, right, that the area under the curve represents the displacement, or how far that object went during that portion of the graph. Now, we don't have one singular shape. We would have to break up this area into 2 separate shapes. And that's why I said the total area, the total displacement, would have to be the area of the green triangle plus the area of the yellow rectangle. And I realized that I got my subscripts messed up. I apologize for that. Here, let's do this. Triangle. Rectangle. Or I suppose I could have... Oh, goodness gracious. Hold on. My bad. How about if I just do this? There we go. Yeah. Okay. We know formulas for those shapes in general, right? And in this case here, my white didn't turn out very good. That's just base times height, right? That's the area of a rectangle. So, if we substituted in the values as they relate specifically to this graph, for the yellow rectangle, the base of this graph is the distance from here to here, and that's the time. The height of this graph is from here to here, and that goes from 0 on the y-axis to u. That's the initial velocity. So to find the area of this rectangle as it applies to this graph specifically, we would just multiply u times t. The green one is a little bit more complex, but the base of that rectangle, or the base of that triangle, is still t. It's exactly the same. But the height now, we'd have to work a little equation, right? V minus u, because we have to find just this portion of the graph, okay? So t times v minus u, and then 1/2, because that's how we calculate the area of a triangle. Then, again, I'm not going to hold you responsible for this, but we do a little algebra, and we end up with this expression. S is equal to u times t plus 1/2 at squared. Notice there is another factor missing from this equation. Just like displacement was missing from the previous equation, v doesn't show up anywhere in that equation. All right? So just like that, right? Final velocity does not appear anywhere in that equation. So now we've got 2 relationships between the factors that we use to describe motion, but in one equation we were missing displacement, and in one equation we're missing final velocity. All right, number 3. Let's go orange for this one. Okay? For number 3, okay, the first two equations that we have derived so far both contain t. There's t, and then this one, t actually shows up in two different equations. So what I'm going to do is take this equation here, rearrange it to look like this. Okay, all I did was get t by itself, subtracted u from both sides, divided both sides by a, ended up with that. Now, mathematically, again, I'm not going to show you, I'm not going to hold you responsible, but if we know that t equals this quantity right here, I can take this quantity and substitute it in for t right there, and then substitute it in for t right there. Because we can do that, right? If we have two equations, we can substitute one equation into the other one. There's no real intuitive way why you would do this, but when you plug in this expression for t into this equation into t spots, do a little math, and you end up, right, first we isolate t in the first equation, then we plug it in and do some simplification, and we end up with this expression, right? V squared is equal to u squared plus 2 times a times s. Final velocity squared equals initial velocity squared plus 2 times the acceleration times the displacement. Notice what happened. In substituting this expression for t into here and into here, that gets rid of t in this equation here. Right? So t doesn't appear in that equation at all. So now we have a third equation that relates the descriptors of motion, but again, we're missing one of the ones that we stated on the original slide. And then finally, right, if we come here, equation number 4, see if I can find a suitable color here. I don't think this light blue is going to work. Oh, it's not bad. On the original set of equations, we said there were 3 equations that we used at the beginning. 2 of them were equal to the average. Right? So, if A equals B and B equals C, remember A equals C. And we have a situation like that here. So we can set this equal to this. And when we do that, we end up with this expression here. We rearrange, get S by itself, and we end up with a fourth expression. Now, again, we see that if you look at the equation, there's something missing. A doesn't show up anywhere in this equation, right? This equation does not depend on the acceleration. So, to summarize, we end up with 4 expressions, 4 equations that relate displacement, initial velocity, should add a tail in that, final velocity, acceleration, and time, but each one of these expressions is missing one of those 5. So, these equations of motion, or these suvat equations, do show up in your data booklet, right? And there they are. Okay, so remember the data booklet I gave you like on the second day of school? So these equations will show up on your test, and they'll show up in your data booklet for you to apply to your test. Okay? How do we apply them? How do we use them? Well, all of those expressions, all of these equations contain 4 of the descriptors of motion that we've introduced so far. That means if you're going to use that equation to solve for one of the 4, you need to know the other 3. So, hold on, sorry. That means first thing you should do is determine what it is that you are actually looking for. What is our unknown in this equation? After you've determined what you're looking for, now what do I know? What do I have to work with? And the important part here is that you're going to need to know 3 variables, or you're going to have 3 known quantities in order to solve for the 4th one. Once you have identified what you're looking for and what you have to work with, it's a matter of going to this chart or going to this set of equations and picking the appropriate equation. If we don't know, for instance, right, let's say we don't know the final velocity, but we do know the initial velocity, and we know the acceleration, and we know the time over which that motion occurs, right? Now it becomes easy to find that we should pick this equation. Why? Because it has the 3 things in it that we know and the 1 thing that we don't know, so we can solve for it. So once we've identified what we're looking for and what we know, now we just pick the appropriate equation and solve. Okay? So tomorrow in class, we will work on some practice problems. This is very mechanical. It just takes practice. It takes practice identifying what you're looking for, what you have to work with, and then picking the appropriate equation. So we will practice that in class tomorrow.